Hello, everyone. I'd like to go ahead and get started with our 1:30 press conference about unlikely new tools for spotting clandestine nuclear tests. Our speakers will be, from the right, Joe Helmboldt, and next we'll have Jihye Park, and Dorota Grejner-Brzezinska. So with that, take it away. Did I get the order wrong? All right, take it away.
Okay, thank you very much for this kind introduction. Ladies and gentlemen, welcome to the press conference on unlikely new tools for spotting clandestine nuclear tests. I would like to acknowledge the co-authors of this research program. First of all, Jihye Park, who actually just finished her doctoral degree research in this particular topic. Joe Helmboldt is our collaborator from the Naval Research Laboratory. Ralph von Friis is our colleague from the Ohio State University. He unfortunately were not able to attend. And Jade Morton is a collaborator from Miami University, and Thomas Wilson works with Joe at the Naval Research Laboratory. So let me give you a bit of a background to what is that unlikely tool that we put in the title. So one of them is the Global Positioning System, which I will very briefly describe to you, and we will focus first on telling you how GPS can actually spot or help us spotting clandestine explosions, and then Joe will introduce the second unlikely tool, which is a very large array. I'm sure all of you are aware of what GPS is, the Global Positioning System, which was designed very many years ago, back in late 60s to early 70s, when the program started. And at the onset of GPS, there was no intention whatsoever to have any usage of civilian side of the system. As you can see, this is the motto which was adopted by the Joint Programs Office. Had nothing to do with what we use GPS for these days. And if you have your phones with you, you're very likely to have a GPS chip, which is probably $50, not $10,000, as was in the previous slide, which was the target cost for the receiver. You can see GPS everywhere. We navigate aircraft, we navigate cars, we navigate humans, we navigate and locate assets, electric grids, banking system. Everything is coordinated by so-called GPS time system. One of the growing or the largest users right now is precision farming. And again, the military applications for which GPS was designed is probably roughly 5 to 6% of all the applications or usages of GPS. So navigation and location of all sorts of things and people is the primary aspect, but there is more. GPS is the system of satellites flying quite high, about 20,000 kilometers or 13,000 miles above the ground, and therefore the radio signal sent towards the Earth travels through atmospheric layer. And certainly the radio signal, radio frequency which GPS uses would be disturbed by ionospheric layer and the tropospheric layer. So as a matter of fact, we were doing research trying to figure out how to improve positioning using GPS signals by removing the most effectively the disturbance which comes from ionosphere. This is what you can see actually on this chart. You can see that the signal bounces off all the charged particles in the ionosphere and therefore arrives with a delay rather than a straight path it would have been traveled through if it was a vacuum. So again, we were trying to improve positioning aspect of GPS, and we realized that by extracting the so-called ionospheric delay, which is a noise for the usages of GPS towards navigation and location, that noise became our signal for this particular research. And I will explain in a moment how really that noise became our signal. So you may not clearly see the connection yet, but I'm trying to structure my story that you would see it hopefully very quickly. Let me go back to 1996 for a second to refer to CTBT, which was established by United Nations General Assembly in 1996. It's the Comprehensive Nuclear and Test Ban Treaty. Until now, we have 3 countries which haven't signed CTBT, which would be North Korea, India, and Pakistan. And of course, we know that those are the 3 countries which actually still conducted some nuclear testing after 1996. There are also 5 countries, including our own country, United States, which haven't ratified the treaty yet. Still, of course, some sort of a monitoring system has been established, and the system is called the International Monitoring System, or IMS for short, and it includes a number of methods, seismic, hydroacoustic, infrasound, and radionuclide detection methods to detect any sort of atomic explosions. The map shows you the distribution of all sorts of types of the sensors used by CTBTO, and you may notice that actually, if I have a mouse here, any pointer, you may notice the areas over here and over there, which we still may expect, as conducting some tests, there is not that much of sensors placed over there. So clearly, there might be a need for additional type of system, independent system for detection and verification. Moreover, as have been observed in 2009 North Korean explosion, the radionuclide network hasn't noticed any xenon-135, the noble gas, which is usually considered 100% proof that there was a nuclear explosion. So, say in 2009 explosion, radionuclide network didn't really sense any xenon gas. So this really kind of motivated us, knowing that sometimes maybe some tests go undetected, to see if the noise we have in GPS signal can somehow help us to get the inverse solution and try to figure out what we can learn about location of the clandestine explosion. So what we literally do, we take GPS signal and we extract so-called ionospheric signal or ionospheric delay from the GPS signal of any stations which would be around the area when the explosion happened, and we try to analyze the signal, ionospheric delay, and try to see if there is any specific signature which will indicate some local disturbance to ionosphere. And just to give you a flavor of what is the sample we are dealing with, if you look at the 1996 and onwards, there were only four events that happened, and we actually tested pretty much, well, 2 of them, the Korean events, trying to use our method to detect and discriminate nuclear explosions. But if you look at roughly 1985 as the time where about half of GPS constellation was up and running, we have about 250 tests to still go through and see if we can prove the method even further and develop a better algorithm based on larger sample. This is the map which shows you the snapshot of locations. Each red dot is the multiple, refers to multiple testing, so the red dots refer to areas which actually conducted any testing, nuclear testing past 1985. So you can see there is still a number of them. Now, what is the new tool we are bringing up? This is GPS, or GNSS, if you will, Global Positioning System, expanded by the European Galileo, which is the new system upcoming, hopefully in the next few years, to full operational capability. There's a Russian GLONASS, there's Chinese Beidou and Compass, plus Japanese QZSS, and plus. There will be a number of satellites we will see, probably up to 120 or so in the next few years. A huge number of satellites, similar to GPS. And what you see on the map is actually a set of permanently tracking stations which were set up by scientists and government. And those tracking stations observe GPS satellites 24/7. And those stations were the source of information for us to develop a method of the detection of clandestine explosions. Those stations operate in real time. We can get data streamed to any laboratory anywhere, whatever has an internet, and you can get this data. Now, I want to say this system comes free to any users, so it's actually a value added, as we can see, to international monitoring system. So now I can formulate, try to maybe combine the 2 threads in my storyline. One was GPS, the other one was the detection of UNEs. And I mentioned to you that, of course, the GPS signal is subject to the disturbance through ionosphere, but at the same time, the explosion which happens underground or on the ground or in the air will actually interrupt ionosphere locally, and this starts and the wave which is created from this interruption or disruption is going to propagate across ionosphere, and certainly at certain point is going to cross the path with GPS signals. So by tracking those disturbances that we can try to detect in GPS signals, we can solve the inverse problem to find location of the explosion. As you can see in the cartoon, GPS satellite is happily moving in the sky, and let me try to pay it back. And we have the location which observes the satellite. There is a representation of the ionosphere. Of course, it's been collapsed to the very thin layer, but in essence, it has a thickness. But for the pictorial representation, it's easy to show that one. Let me play again. So what happens? Notice we observe ionospheric signal. It's kind of a quiet signal, but the blast happens, and at certain point, the blast reaches the IPP, which is the point related to the piercing of the signal from the satellite to the station through ionospheric layer, and this is when we see this big jump in the ionospheric signal, and this is an indication to us that something happened. And I'll ask Jihye to continue from here to explain to you how the network of stations can use this geometry to actually get the solution.
Okay, as Dr. Brzezinska showed the previous slide, the previous slide explained how the underground nuclear tests affect the ionosphere of GPS observations. And this graph, this diagram draws how to determine the location of the origin, the point source of that is underground nuclear explosion using the observation of the ionospheric observation of GPS. So suppose we have many stations on the ground and observing the many multiple satellites, so like real world. So we can see that there's stations and satellites observing the GPS signal from the space. So what we can do is compute the observe the ionospheric pierce point. That is, we can have the three-dimensional coordinate of the IPP points, and if we observe the IPP points coordinates with the time of arrival from of the signal from the point source to the IPP, then we can inversely compute the location of the underground nuclear explosion position like this way using the geodetic method. So the computation of the location using the multiple observation of the traveling ionospheric disturbances is actually very similar to the seismic determination of the epicenter like these graphs. So the plot in the right figure shows that you can see the black dot in the middle, which would be the epicenter of the earthquake. And you can, if you observe the seismic signal from the stations, multiple stations like A, B, and C, like here, then and you can guess the proper. You can compute the epicenter of like this black dot using the propagation speed of the seismic signals. So this plot shows that the horizontal axis of this plot is the distance traveled from the earthquake epicenter observed by station A, B, and C, and the vertical axis is the time elapsed after start of earthquake in minutes. This graph shows that this is pretty much similar to the previous slide's graph, that you can. This is a GPS detection result of travel time and distance model of the UNE-induced traveling ionospheric disturbance observations. So those two plots are, one is the Hunter's trophy induced by the United States in 1992, and the other one is the divider, which is also induced by the United States in 1992. And there's the data points indicates the observations of traveling ionospheric disturbances using the nearest station, GPS stations at the time of the explosions. And the horizontal axis is the time of the propagation of the signal, and the vertical axis is the distance from the location of the explosion to the ionospheric pierce point that from each station, GPS stations. And you can see that the propagation velocity indicated as the fitting model is nicely fit within the confidence interval of 95% of confidence interval. And the propagation velocities of Hunter's trophy is 573 meter per second with the standard deviation of about 85 meter per second. And the other one, the divider, is propagated with the speed of about 740 meter per second with standard deviation of about 135 meter per second, respectively. And the Hunter's trophy event, the velocity of the Hunter's trophy is verified with the very large arrays of observations that will be presented by Dr. Joe Helmboldt. So this is the comparison of the traveling ionospheric disturbance waveforms. That this is very important to discriminate the underground nuclear explosion signature from the other sources, because the ionosphere can be disturbed with other sources, such as the earthquake, as I explained briefly. So those first two plots are the signature of underground nuclear explosions back in the 2009 and 2006, induced by, conducted by the North Korea. So you can see the similarity between two signals highlighted in red. And the last one is the signature of the signal of the earthquake, Tohoku earthquake in 2011. And you can see the difference visually in terms of the wavelengths and the amplitude of each signals. And also, we investigated the discrimination method, not only in the time domain but also the frequency domain, how to discriminate the underground nuclear test event signal from the other sources, that is earthquake. So I will stop here for the GPS part and pass it to Dr. Joe Helmboldt.
So I'll be talking about the second instrument that's being used to do essentially the same thing, or a similar technique to look at the ionospheric response to this explosive test that was done in Nevada. Our group at the Naval Research Lab are primarily radio astronomers, but we have to do almost the exact same thing that the GPS has to do, which is to correct for ionospheric distortions. We're looking at, instead of satellites, we point up at cosmic sources, usually other galaxies. But the signal has to go through the exact same ionosphere that a GPS signal goes through, and it causes similar distortions that we have to correct for. And one of the instruments that we primarily use is the Very Large Array in New Mexico, as you may be familiar with. If you've seen the movie Contact, then you've seen pictures of this telescope. It's actually referred to it as a single telescope, but it's actually made up of 27 different radio dishes that work together, and we combine the signals received by these antennas in such a way that we can process them and make an image, a very high resolution image of radio sources You essentially get the same resolution you would with a dish, a single dish that's the same size as the entire array. It can be configured in 4 different configurations. This is a picture in the most compact configuration. It's the easiest one to take a picture of. It only spans about 1 kilometer, and there are little railroad tracks that run along here, and about every 4 months the telescopes are moved, and out to the largest configuration spans almost 40 kilometers. As you can see in the picture, all but 1 telescope which is being serviced, these are all pointing in the same direction. They're all pointing toward the same source. But since they're spaced apart, they all point through a different part of the ionosphere. So if there are fluctuations in the ionosphere induced by something like, say, an explosion, that's going to distort any image we try to make, because each telescope will see a slightly different part of that disturbance. So it has to be corrected for. And similar to the Ohio State program, we've been looking at taking those corrections and actually turning it around. What we see as noise is becoming our signal, and we're to learn more about the ionosphere. And so we paired up with the group from Ohio State and tried to find one of these nuclear tests for which we had both GPS and VLA data. And it turns out that the Hunter's Trophy event in 1992 is close enough in Nevada that we could see the effects from the VLA, and it just so happened that someone was observing during that time, the telescope happened to be in the D configuration, which for this program is not ideal because it's very compact, and so it doesn't see, the difference in the ionosphere between adjacent telescopes is not large, but we were still able to detect the disturbances that went over the telescope. We couldn't actually watch the disturbance itself, the main disturbance from the explosion pass over, because the array was so compact it moved over the array in about 2 seconds, which was basically too fast to see. But we could see the effect of that disturbance on the ionosphere. And so to illustrate that, I'll show you the data product that we produce when we analyze our data from the VLA. Basically what we do are we look at the fluctuations that we see from each telescope and then try and map out where those fluctuations were traveling in terms of direction and size and speed. And so these little images here show you basically a map of fluctuation power, how much, what percentage of the fluctuations were moving in a particular direction. So these are just like a map. North is up and east is to the right. And this is basically showing you, we detected the UNE went off at about 1700 hours UT. Before that, we detected fluctuations, but relatively speaking, they were very, very weak and had no particular preferred direction. But closer to the time, sometime after the explosion, we start to see a pattern emerge in these maps, and then that pattern is sort of frozen in for the rest of the observation. And as we move forward in time, it gets larger and larger. And so we're seeing basically this disturbance has passed over the array, the telescope, and has basically stirred things up, and the fluctuation amplitudes are much, much larger than they were before. And the time when it arrives is very consistent with the speed that was derived from the GPS data. So that's an independent confirmation that what's been developed with GPS receivers is working and is producing something very real, because we've detected it with a completely different but similar instrument. And then what you get from such a compact array that's relatively sensitive to the ionosphere is a little bit more detailed information about small-scale fluctuations in the ionosphere that occur as the wave moves over. For instance, you can see in this little map, these sort of cones here show you roughly the direction we'd expect the main disturbance to be going. And you can see most of the fluctuations, the small-scale things that we detect with the VLA, are actually perpendicular. So this is basically indicates some small-scale structure along the wavefront itself as it moved over the array. So it's a sort of complementary approach to GPS. GPS gives you a very large coverage area so that you can track the wave as it moves, and the VLA can zoom in and examine the details of the finer scale fluctuations that are associated with the wavefront itself.
So just to summarize with the last slide that we have before we open the floor for questions, as you can see, both methods are quite effective in finding the ionospheric disturbance, tracking the ionospheric disturbance, and also finding the underlying source of this disturbance. What is important, the way we think about it, is the algorithms are there. The infrastructure is there, which was, of course, put for some other purposes, but the noise to the actual purpose of GPS network or VLA is certainly our signal to try to focus on this particular problem solution. One important aspect I want to underscore here is that GPS data actually are real-time streamlined to any users, and we can get the processing done in very short time after the blast happens. And again, the GNSS infrastructure is available globally at no cost. This is just value added if you use this for this particular purpose. And we believe that due to the more dense location or even location of the GNSS infrastructure on the ground, this particular infrastructure can fill in the gap, which you can see in the South Asian region when IMS has much smaller number of sensors. Again, we just demonstrated to you the research algorithm, the research solution. There's a little bit more research work which would be needed to make this approach operational, but we believe that this can happen. Thank you.
Rick Lovett, freelance. That was interesting. I'm missing a step in this, which is what happens when the nuclear explosion occurs that interferes with the ionosphere. What does the nuclear reaction do physically to produce the wave?
Oh, the mic is on. It's on. So what happens is when the blast happens, so-called gravity acoustic waves are happening. So the gravity acoustic waves propagate on the surface, right, and underground, if I'm not mistaken. I'm not a seismologist, but this is how I understand it. And this actually has an impact on the upper atmosphere.
So this is like the way they've done this to track tsunamis?
Yes. One of the examples is tsunami or earthquake is similar method, yes.
Hi, Larry O'Hanlon with Discovery News. He had the same question I had, which I'm glad he... But I had another couple of questions. Would this be... Do you conceive think of it as being used in conjunction with seismic data as another confirmation? I know that seismic data is one of the big ways that people watch for this now. So it would be just to add to that, to help confirm for, say, a test?
You guys want to speak to it? Well, the way we take it really is an additional verification method, right? Because seismic is de facto the king of the methods used by IMS, I should say. Maybe I shouldn't say that, but there's lots of seismometers, and this is the primary method of detection. But GPS provides independent verification. The whole point is it's a very dense network. The data are free. We have the algorithm, and it's easy to do that. So it's not replacing anything. It's just additional verification and discrimination. Because we can discriminate between the earthquake and between the signature of TID would be different, what we see in GPS signal from earthquake or from the UNE. So we have this aspect of discrimination as well, not just location.
Is that different? You have a different way of discriminating?
Yes.
Oh, that's
Yeah.
that's
right.
good. The other question I had was: are there any other than earthquakes? Is there anything that gets in it's noise like this? Any other things that cause this? Like tsunamis came up, but any other phenomenon that would cause this kind of thing?
Joe, want to talk to it?
Well, actually, the TID, traveling ionospheric disturbance, is a fairly common thing. And there are different types that are excited by different mechanisms, but the main difference between these and what you get from an earthquake as well is that these will start from a very particular point and go radially outward. Whereas other TIDs, they're plasma waves that form in the ionosphere. So among TIDs, these kind of are fairly unique.
Horst Rademacher, Frankfurter Allgemeine Zeitung in Germany. I have a question about the physics of this whole traveling wave. You showed some wavelengths and you showed some velocities, and there were major differences. I think there was 500 meters a second at 700 meters, and the wavelengths were 4 millihertz and 16 millihertz or something. So how come they are so different if it's the same physical phenomenon?
I suspect that it has a lot to do with what's happening in the ionosphere at the time, because the ionosphere is not just a quiet, stable layer in the atmosphere. It's dynamic to begin with. And so this is an interaction. There are probably lots of nonlinear processes that go on. You've got this disturbance wave energy that propagates upward and hits the ionosphere, but the ionosphere already has things happening in it already, turbulent fluctuations, possible other wave-like fluctuations. So it's not such a straightforward problem to say that you're always going to get the exact same looking wave every time. It probably will be somewhat unique in terms of duration and amplitude between a UNE and an earthquake, but it's probably going to be a little bit different every time depending on what the ionosphere conditions are.
May I have a follow-up? If that's the case, how can you then easily distinguish between nuclear explosions and other things? I mean, if the variation or the variability of nuclear explosion signatures in the ionosphere is that large, how can you then say, oh, this was a nuke test and this was a meteor blasting through or whatever? I mean, you talk about the discrimination. How can you be sure that it's a nuclear test then?
Well, the first order thing is that you can track it. You can use multiple GPS stations to basically do the inverse problem and track it backward to a specific point. And GPS fairly frequently will observe a TID or some kind of disturbance, but it's not originating from a particular location. So if you run this algorithm on it, it would fail. You would get no location because it's not a UNE. But you would get the same result but an earthquake would give you the same sort of, the fact that it originated from one point. But from the preliminary work that Jihye has done, it looks like that the actual duration and amplitude are different. So the exact details, what the wavelength is and so forth, may vary a bit, but the general characteristics so far seems to be consistent.
Let me add a little bit about the velocities of the TIDs. Actually, we found that two different velocity from the U.S. events, like Hunter's trophy and dividers, and they are pretty much faster than we found from the 2009 North Korean UNE, because we published the paper that we found the signature from the 2009 North Korean nuclear explosions, and what we observed, what we computed was less than 300 meters per second of velocity, propagation velocity of the signal, which was, we guess that the explosion yield was pretty different, because this case much bigger yield, up to 20 kiloton of yield, explosion yield, while the North Korean explosion was less than 5 kiloton yield. And from the bunch of literature said this kind of local scale disturbances can be classified like a medium scale or small scale TIDs within, and roughly they could be more than several hundred meters per second up to less than 1 kilometer per second for that kind of local disturbances, while the bigger disturbances of like geomagnetic storms or earthquake, a big earthquake would be faster, generating the faster bigger energies, that is more than several kilometers per second of propagation velocities.
Tia Ghosh from Life Science. So what I'm wondering is, can the Very Large Array detect things that are farther away? I mean, Hunter's Trophy is pretty close to New Mexico, and there are types of telescopes that are equipped to do this type of detection, or is this basically like the only one that you can imagine doing this?
The only test I've looked at was the 2009 test in North Korea, and someone happened to be observing with the VLA at that time, and I didn't see any evidence of it. So it's probably too far away. There are other telescopes like the VLA. There is the giant meter wave radio telescope in India, which operates at similar frequencies and would be just as capable of detecting this disturbance. There's a new telescope in the Netherlands, which is called the Low Frequency Array. It's being commissioned now and it would likewise be capable of doing so. And then there is a larger project called the Square Kilometer Array. The actual SKA will be in South Africa, but there is a telescope being developed in Australia that's sort of a precursor. That will also be so. In a much more coarse sense, there will be sort of global coverage of these types of telescopes.
Let's see, I want to come back to the question of distinguishing earthquakes because you used a very powerful earthquake, and earthquakes produce, they vibrate the ground for a long time, whereas I suspect that your nuclear blast is a much shorter duration blast. So I'm wondering whether you can distinguish a smaller earthquake or whether it would look like a blast.
Yeah, that is really good question because that's our question too. So we are working on the smaller case of earthquake right now. But what we can say is when you detected the TID from the underground nuclear explosions, we were not only just observing the peaks, but also we also computed the correlation properties between the wave signatures. So we are working on the smaller scale earthquake, but what we expect it would be is that the proper properties of wave would be separable. But right now we just say that we are still working on that.
David Hirsch with NHK Television. Excuse me. I wonder, is detection possible in the absence or failure of the other elements of the IMS system? And how practical is it to have a well-concealed UNE that would require something like this? And to the first question, I guess, is it only that it could be used as a validation, or assuming that it was the only system that was deployed, could it detect on its own?
Well, to the best of our understanding, GPS is not a part of the IMS, and it would have to be formally accepted, right? So this is just, like I said earlier, a value-added mechanism which can confirm. But in a case that nobody else can see it and GPS does, it would be probably a little bit tricky because seismometers at least should see it. The only case we know of that, for example, the radionuclide method didn't see a xenon gas, which, like I said, is a must for any nuclear explosion, was the 2009 Korean explosion. It was so well concealed that there was no xenon gas apparently seen. So sometime later, there was some detection in northern Canada, but it was so close to a hospital that it wasn't certain if the xenon came from hospital or somewhere else. So I don't think I really have a direct answer to your question because, like I said, GPS is not a method which is approved by ISM. And frankly, I would say I don't expect that GPS would see what seismic doesn't see. If it's a very, very small yield kind of a test of very weak earthquake, both methods may have a problem discriminating. We haven't tested this. As Jihye said, we are looking into this, but I know that seismologists are asking the same question to themselves.
I think maybe another way to think of it is if this releases a lot of energy, and if you were able to devise a way to mitigate how much energy goes into, say, the crust, the Earth, the energy has to go somewhere, and you'll still see it go up into the atmosphere. And so they're sort of complementary. One's monitoring the amount of energy that's put into the ground. One is monitoring how much energy is put up into the atmosphere. And to think that you could stop both of those things from happening at once is pretty, I don't see how you would do it. So they could work very well together, potentially.
Okay, we have time for one more question. Okay, I guess we don't have another. Thank you, panelists, very much for your talking with us today, and thanks everyone else for being here. I would also like to ask if you're going to do any follow-up interviews, if you could take them out of the room and do them outside. Appreciate that. Our next press conference is at 2:30, and it's Science and Technology at Extreme Depths with James Cameron and the Deep Sea Challenge scientists.